Control of complex nonlinear dynamic systems with incremental deep learning neural networks. Here we present the problem we work in this paper. We have a dynamic system and we want to train a neurocontroller so that the system behaves in a desired way. Several control problems can be solved with neural networks: stabilization, regulation, and tracking control problems. The important point here is that for training the neural network, we will take into account the dynamics of the control problem. The dynamics means that the output of the system becomes input in the next step and also becomes input to the closed loop system in the next step. Problem definition. The system is given by this state space equation, where X is the state vector and U is the control input. We want to find a state feedback neurocontroller given by this expression for minimizing the quadratic cost function given by this expression, with Q and R being positive matrices. After this problem is complete, we want also to train a static output feedback neurocontroller given by this expression. It's a neural network with U depends on the measured output Y, and the measured output Y depends on the state vector X. We want to train this neurocontroller, and the weighting coefficients BNLView will be found for minimizing the cost function J. For that, the weighting coefficients will be updated using the total partial derivatives of J respect to W, J respect to B, using the steepest descent algorithm. For computing these total partial derivatives, we will use this expression calculated from the definition of J presented before. Here we can see the total partial derivative of X respect to W and of U respect to W. Now we will present how to compute these total partial derivatives. And for that, we will use the dynamic backward propagation algorithm DBP. This figure shows the time deployment of the control process. Here we have the neurocontroller and the system for step 1, for step 2, for step 3. If we analyze the dynamics of the control process, we can formulate these recursive expressions for computing the total partial derivatives. Here, the total partial derivative of X at time k plus 1 can be computed from the total partial derivative of X at time k. It's a recursive expression. Here, the components in blue color are computed from the system model, and the components in brown color are computed from the neurocontroller. Here, we also show the expression for computing the total partial derivative of control input U respect to W. It depends on the total partial derivative of X respect to W. Here we can see the simple partial derivative, and this is the total partial derivative of U respect to W. One important point when training neural networks for controlling dynamic systems is incremental learning. Similarly, as human beings, neural networks have to be progressively trained, starting from easy tasks and continue with more complex tasks. Learning is more visible to converge if we start from easy tasks, and the weighting coefficients obtained from this simple task are afterwards used for training the controller for more complex tasks. We will present here 2 examples about the meaning of simple tasks. Imagine we have to train a neural network for controlling a dynamic system working in a wide range of operating conditions. This wide range of operating conditions could be a wide range of initial states, and these initial states of the system must converge to a final decided values. At the beginning, we will start with initial states very close to the desired convergence values, so that learning is much more simple, the convergence is much more feasible. After we train the neural network for this condition, we continue training the neural network with initial states farther from the desired conversion values. After that, we continue with farther and farther initial states until finally we cover all the desired range of initial states. Also here, we have the problem when we want to train a neural network for controlling an unstable system. First, the state space equation of the unstable system will be modified to have an unstable system. And we train the neural network for this stable system. And after that, we continue training, but making this stable system more unstable, more unstable, more unstable, until finally we recover the original unstable system. In this way, we can train neural networks to work in a wide range of operating conditions and for highly unstable nonlinear systems. We will present some problems we have worked using the dynamic backpropagation algorithm with incremental learning. Here we have a bilinear system. It's a weakly bilinear system. We have matrix A, and we want to train a neural controller for stabilizing this system so that the state variables, starting within this range, initial values of state variables, these variables will converge to the desired final state 0, 0. We will apply incremental learning regarding initial states. At the beginning, the neural network will be trained considering these initial states, which are very close to the desired final state. After this training is completed, we continue with this set of initial states, which is further from the desired final state. After this training is completed, we continue with further and further initial states until finally we cover all the range within the desired range of operation of initial states. Here we show a second problem. It's a highly unstable bilinear system. In this case, matrix A is highly unstable. And again, the problem is to train the neural network, the neural controller, so that the system, starting from initial states within this range, the state variables converge to the final decided states 0, 0. Here we will apply double incremental learning. One incremental learning from initial states, as we shown before, and also one incremental learning from for matrix A, starting from stable to unstable, or from weakly unstable to highly unstable. Here we have matrix A. We start the training with this matrix A. We train the neural controller, and after that we continue training the neural controller with this matrix A. We change matrix A until finally we recover the matrix A of the original unstable system. Here we present the results of the highly unstable bilinear system with neural control. Here, green line and blue line corresponds to the system state, and the red line to the control input. We see that both states converge to 0, decided state 0, starting from different initial positions, different initial states. After this training is complete, we can use the same neural network for tracking control. In this case, we change the inputs. The input now will be x minus x asterisk, where x asterisk is the decided state vector, and the output will be u minus u asterisk, where x asterisk and u asterisk must satisfy this convergence condition. Neural networks can also be used for output feedback static neural control. Here we have a system with 2 state variables, but the controller will have only one measured output, which is input to the controller. The idea here is to train the neural controller using the same algorithm, dynamic propagation with incremental learning, but having the controller as input only the measured variable y. Since the system model is known, this model can be used to compute the complete state variables along the training process for calculating the total partial derivatives. In this way, we can implement the training process using incremental learning and complete the training of the neural controller. We have also applied the neural control for the autonomous position of mobile robots. Here we have a mobile robot working in this area. The robot can start from several initial positions, and the objective is to reach this final decided position. These equations represents the motion equation of the mobile robot. X and Y are the coordinates of the center of the rear axis. Theta is the inclination angle of the robot, and delta is the steering angle of the steering wheels, front wheels. and is the control input. R represent the distance of the robot moving at each step. The distance the robot moves at each step. In this problem, the desired final position is given by x asterisk equal to 0, y asterisk equal to 30, and theta asterisk equal pi over 2 equal 90 degrees. Here we can see that the robot is a non-holonomic system. We see that coordinate x asymptotically converge to 0 to the desired state. Also, we can see that the inclination angle theta asymptotically converge to the desired value pi over 2. However, coordinate y does not converge asymptotically to the desired value 30. In this way, we will use only two variables for feedback control, x and angle theta. The dynamic backpropagation algorithm will be used with incremental learning strategy for training the neural controller. And here we show the results, and we can see that the neural network is able to control the mobile robot so that the robot achieves this desired final position starting from different initial positions. After this problem is solved, we will use the same neural network for tracking control by properly changing the inputs and output of the neural controller as it was shown before. Here we show the results of the autonomous motion of the mobile robot. In this figure, we have the motion from different initial positions to different desired positions. And here we also show the trajectory of the mobile robot following with high accuracy a circular trajectory. These results verify the effectiveness and the performance of neural networks for the control of complex nonlinear systems. We have applied the dynamic backpropagation algorithm and implementing an incremental learning strategy. With this, I complete my presentation. Thank you for your attention.